Welcome to The Explainer. I am absolutely thrilled to guide you through today's topic, because it is going to fundamentally flip how you think about the future of technology. Today, we're diving into this really fascinating structural analysis by futurist and economist Thorsten Mayer. Now, for years, we've basically been told that the global AI race is a battle of silicon, right? It's all about who can build the absolute fastest, smartest computer chips. But Mayer argues that this paradigm has completely shifted. The binding constraint on artificial intelligence, it's actually no longer computing power. It's electricity infrastructure. We're going to explore how the US and China are taking radically different, structurally opposed approaches to powering the AI revolution. Okay, let's dive into this. Here is the cognitive roadmap for our explainer today. We're going to start by defining what gigawatt scale actually means, then we'll look at the American workaround stack, followed by China's centralized buildout. From there, we'll unpack a super interesting concept called asymmetric substitution, explore whether efficiency can save the day, and finally, wrap up with the future of global AI policy. I want to start by anchoring us with this genuinely provocative quote straight from Mayer's essay. He writes, "Chip performance is no longer the binding constraint on AI deployment at frontier scale. Power is." You see, the United States dominates the AI stack. We're talking chips, infrastructure, models, applications, the whole shebang. But Mayer makes the case that the US does not dominate the physical layer that actually delivers electrons to that silicon. And to really grasp why, we first need to wrap our heads around the entirely new scale of AI. Which brings us to Section 1, the gigawatt scale reality. So what does a modern frontier AI data center actually look like heading into 2026? Just a few years ago, a 100 megawatt facility was considered massive. Today, 1 to 2 gigawatts is the new sweet spot for a single frontier training site. And honestly, anything larger than that and the sheer physical distance between the servers starts causing network latency issues. But tech giants are pushing the envelope even further by clustering these sites together. Take Meta's Hyperion campus in Louisiana, for example. They are targeting an unbelievable 5 gigawatts across a physical footprint the size of a significant chunk of Manhattan. And OpenAI and AWS, they've got multi-year targets pushing 10 to 12 gigawatts. Let's ground that massive abstraction into human reality for a second. At 1 gigawatt, a single AI data center consumes roughly the same amount of electricity as a city of 750,000 people. A 1.2 gigawatt site's peak demand, that's half the peak system load of El Paso Electric. So those hundreds of billions of dollars tech companies are pouring into this, they aren't constrained by money anymore. They're constrained by sheer physical reality. It's literally about the rate at which we can physically build transformers, permit transmission lines, and hook up new power generation. Moving right along to Section 2, the American workaround stack. So how exactly is the US dealing with this massive energy appetite? Well, consider this staggering number: 2,300 gigawatts. That is the amount of generation and storage capacity currently sitting in the US interconnection queue, just waiting to be connected to the grid. And it carries an average wait time of 5 years. The US grid was simply not designed for gigawatt-scale, hyper-localized AI load profiles, and a regulatory structure definitely wasn't built for this kind of urgency. And this brilliantly illustrates what hyperscalers are doing about it, because they absolutely cannot wait 5 years. They are just routing around the public grid entirely. They're doing this in 3 main ways. First, behind-the-meter nuclear deals. Think Microsoft's deal to literally restart a unit at 3 Mile Island exclusively for their own use. Second, off-grid gas turbines. Yes, they are trucking in massive gas generators to run cutting-edge AI completely independent of the grid. It is a total brute force workaround. And third, they're moving to Texas, where the ERCOT grid operates independently of federal FERC jurisdiction, which means way faster interconnection times. It is wild how fast this shift is happening. Back in early 2025, virtually all data center power flowed straight through the public grid, but by early 2026, projections show nearly 30% of new data center capacity is being designed to operate completely independently of the public grid, using on-site generation. The hyperscalers aren't fixing the grid bottleneck, they are bypassing it to build their own private power islands. Now, let's look at Section 3, China's centralized power buildout. We have to look at the other side of the global equation, which operates on a fundamentally different structural foundation. Let's just let the numbers speak for themselves here. In 2025 alone, China added more than 430 gigawatts of new wind and solar capacity. The US? We added about 36 gigawatts. That is roughly an 8-fold difference in a single year. China's AI infrastructure is sitting on top of a renewable generation buildout that honestly has absolutely zero historical precedent. China organizes all of this through a centralized mandate known as the Eastern Data Western Compute Initiative. Instead of fighting for grid space in their really dense eastern cities, they route AI computing demands straight to Western renewable energy hubs. And they connect them using the world's most extensive ultra-high voltage, or UHV, transmission backbone. We're talking about over 40,000 kilometers of lines that can move green electricity from a desert in the west to a city in the east, a distance of 1,500 kilometers in just 5 milliseconds. 5 milliseconds. That speed is just mind-bending. This takes us directly into Section 4, the asymmetric substitution strategy. So the crucial point is how this massive power infrastructure enables what Mayer calls asymmetric substitution. It's the core thesis of this whole explainer. This is exactly how China compensates for the fact that its domestic AI chips are technically inferior to cutting-edge US chips. Because they have this vast, unconstrained power and transmission infrastructure, they can afford to just throw massive amounts of electricity at a much larger number of less efficient chips to achieve comparable system-level results. It's a classic underdog tactic. Let's break down the hardware reality for a second. The absolute top-tier US chip, the NVIDIA H100, is banned from export to China. Huawei's domestic alternative, the Ascend 9110C, operates at about 60% of the H100's inference capability. However, the 9110C actually beats the degraded chip that the US does allow into China, which is the NVIDIA H20 on both power efficiency and processing capability. So what does China do? These specialized network architectures to string hundreds of these domestic chips together.
And this creates such a fascinating divergence in binding constraints. The US optimizes for performance per watt because our grid is basically maxed out. China, on the other hand, substitutes raw watts for chip performance because its power generation scales way faster than its chip limits. So you have the US with better chips but a constrained grid up against China with constrained chips but a totally unconstrained grid. Which naturally leads us to Section 5. Can efficiency close the gap?
Now, what's really interesting about this slide is the core question it asks. Can American innovation in silicon and algorithms mathematically override China's physical infrastructure advantage? This is arguably the ultimate technological question of the decade. We know for a fact that models are getting more efficient. The energy required to process 1 million AI tokens drops dramatically every single year. But does that actually solve the US grid problem? The math here is pretty brutal. To structurally neutralize the gap, assuming China keeps building 400 plus gigawatts of renewable power a year, the US has to compress AI workloads onto 60% to 80% less power over the next 3 to 5 years. But here's the catch. Efficiency gains accrue to both sides. When a major algorithmic breakthrough happens, like we saw with the highly efficient DeepSeek models coming out of China, everyone benefits from it. Efficiency definitely slows the divergence, but it doesn't fundamentally reverse China's raw power advantage. Let's move to Section 6 and see how this all builds into the future of AI policy. Ultimately, what we are looking at isn't just an engineering problem. It is a massive industrial policy problem stemming from entirely different models of governance. The US operates on layered fragmentation, right? We've got federal agencies, 50 state utility commissions, and local zoning boards. That ensures local accountability and democratic legitimacy? Absolutely, but it moves incredibly slowly. China operates on a centralized mandate. A single planning commission aligns the data centers, the renewable generation, and the transmission lines all at the exact same time. It achieves massive scale and speed, but it sacrifices local accountability. Both of these systems have very real, very tangible trade-offs. So Mayer outlines 4 potential paths forward for the US AI sector. Path 1 is statutory acceleration by Congress to fast-track grids, though, let's be real, that's not currently on the table. Path 2 is permanent behind-the-meter routing, where tech companies just keep building private power islands, and right now, this is our default trajectory. Path 3 is moving US compute offshore to places with power, like the UAE or the Nordics. And Path 4 is just hoping that efficiency gains somehow close the gap entirely. And that leaves us with this final, genuinely profound question to ponder. Will constitutional gridlock become a structural ceiling for US AI dominance by the end of the decade? The US clearly leads in chips, models, and applications. There is no doubt about that. But as Mayer so brilliantly points out, if the binding constraint of the AI race is now electricity policy, the entire landscape of global tech supremacy might be decided not in a server rack, but out there in the power grid. I really hope this gave you a totally new lens on the AI revolution. Thank you so much for joining me for this explainer, and keep learning.